Hi again, this is my second video on differentiation, so if you missed this and you wonder where it's coming from, just go and watch my first video, okay? It lasts 30 minutes, but in that 30 minutes I get to where this actually comes from, okay? Why we actually get to that, alright? So what I'm going to do in this video is I'm just going to start from here, okay? So I've just left this up, just as a quick reminder, okay? So when we're using fx notation for defining functions, for example f of x equals x squared, we tend to use this notation for the gradient function. It's f with a dash, f dash x, or f prime x, some people say. Okay? And the general result is when you have a function such as x to the power of n, where n is actually any real number, okay, then the gradient function, written f dash x here, is nx to the power of n minus 1. More commonly though, particularly in A-level mathematics, we use the y equals notation. So for example, y equals x squared. In that case, we use dy dx as the gradient function differentiation, okay? It actually stands for changing y over changing x, as this diagram kind of showed a little bit earlier, okay? So because I've still got it up there, if those are your 2 points, you find the gradient between them, so that's your change in y, that's your change in x, represented by delta y, delta x, and we just use dy dx instead of deltas. There may be another video from me explaining why that is, but not now, okay? So we use the dy dx notation. Obviously these are exactly the same as those, it's just you need to be able to switch between the two different notations depending on how your question or your problem is worded when you're actually attempting it, okay? So let's just move on a little bit from there, okay? So what if, let's just rub this out, okay? What if instead of y equals x to the power of n, you've got another coefficient involved, another number involved. So suppose you've got this, y equals 3x squared. Okay, what is the gradient function of that? Okay, now because we're doing A-level mathematics here, let's just skip straight to the dy dx notation. Okay, we don't write gradient equals anymore. Okay, you might be doing that at GCSE, for example, or year 8 or year 9, but in A-level we're not. We're writing dy dx represent our gradient function. Okay, well, what's it going to be? Well, consider what it was for y equals x squared. Okay, for y equals x squared, dy dx was 2x. Okay, and consider what the 3 is doing to the entire of this function. Okay, you've done your transformations of graphs already, I hope. So when you've got a graph of y equals f of x, how does the same graph, but with a multiplying factor of a in front of it, change the graph? It makes it steeper. Okay, makes it steeper in the y direction. Remember, gradient is all about steepness. Okay, so the factor a there makes the whole graph steeper by a factor of a, so it makes the gradient, of course, increase by a factor of a as well. So this graph, 3x squared, is steeper than x squared by a factor of 3. Okay. And so the gradient is also going to increase by a multiplication factor of 3. So it'd be 2x multiplied by 3, which is 6x. Okay. So when you've got a coefficient in front of the variable, okay, that's all you're doing. The quick way of looking at it is this. Okay. You just do 2 multiplied by 3 to get you 6. Okay. Let's do another one. So what if you've got instead y equals 7, x to the power of 4, what would dy dx be? It would be 28, x to the power of 3. You used to do 4 times 7, 28, x to the power of 3. Okay? And that's going to lead on to my next result, which is one that you'll want to write down if you're taking notes on this. Do you take notes in these videos? I don't know. I just hope you get something out of it. That's all really. And if you're just using it for revision, yeah, so be it. Great. I mean, it's not a bad way to revise, is it? By just watching some maths. So I'm going to write this as k x to the n, okay, where k is any constant value. Okay, and then the gradient function dy dx will be k multiplied by n, x to the power of n minus 1. So just do n multiplied by that. Just write it in alphabetical order, that's all. Okay, so that's rather an important result there. Okay, and I've said that works for all real values of x. So let's just put that to the test, shall we? Okay. Suppose we look at this function here, y equals x to the power of 1. Which is just y equals x, okay? So my previous video, I didn't consider that. I said at the beginning something along the lines of working out gradients of straight lines is easy, okay? Because you did that at GCSE. Well, you know the gradient of y equals x is a 45-degree line, and if you compare it with the equation y equals mx plus c, work out the gradient of y equals 7x or 2x or 3x is pretty simple. You just write down what the coefficient is, that's the gradient, isn't it? But using this rule here, okay, let's write it as y equals x to the power of 1. You get dy dx is equal to, bring the power down, 1 times x to the power of 0, which of course is just going to be 1. Okay. If I have a different equation, like y equals 5x, okay, then dy dx is just going to be 5. Because you know, looking at this, that the coefficient of x is just going to be the gradient, okay? But then using this rule here, I'm just showing you that it still works when you're x to the power of 1, okay? You do 1 times 5, which is 5, and then x to the power of 0, which of course is just 5, okay? So even though I just considered this for x squared, x cubed, x to the power of 4, and so on, it still works for linear functions, okay? And of course it works for negative values and for fractions as well. So let's just see how it works for fractional values first, shall we? So when you've got x to the power of a half, what is dy dx? Just exactly the same process, okay? You just put the half in front, so 1/2, and then decrease the power by 1, negative half. That's it, okay? For the time being, just write these in index form, okay? Of course, you could write this as y equals square root of x. You need to be aware they're the same. And of course, when you rewrite this, you could say that dy dx as a fraction is equal to 1 over 2 root x. Because the half, of course, written like that, 1 over 2, and x to the negative half means 1 over root x, 1 over x to the half, so it's written like that, okay? But just for the time being, just write it in index form, and that is fine, okay? Suppose I put a number in there like a 7, okay? How's that going to change? It's quite simply, that's going to be 7, okay? So half times 7, 7 over 2, okay? And so I'll just change this by saying that that was maybe equal to 7 root x, just squeeze that in there, and this will change to 7 over 2 root x. So exactly the same rule applies there, okay? If you can, well not if you can, please do write as top-heavy fractions, okay? Because it's going to be much simpler for you, okay? Let me just give you an example of top-heavy fractions. Suppose you've got y equals 3/4 x to the power of 3 over 2, because those are sort of things that you're going to have to differentiate, okay? Then dy dx is equal to, I don't know, maybe just pause the video and do it, and then unpause it, okay? Or maybe you've done it already, okay? So applying the same rule, okay? So you could do 3 over 2 times 3 over 4. Can you see how doing that is much simpler, okay, than if you did 1.5 times 3/4, or worse, if you went with decimals, 1.5 times 0.75, 1.5 times. The thing is, it's easy to write it as top-heavy fractions, 3 over 2 times by 3 over 4. So you've got 9 over 8, you see? That's 3 over 4 times by 3 over 2. Remember, just doing top 2, bottom 2, okay? And x to the power of, that's 1/2, isn't it? Because 3 over 2 subtract 1 is 1/2, okay? So that's just a couple of examples of using fractions, okay? Let's use negative values and see how that works with negatives, okay? So let's say this works for all real values, okay? And the way of saying that is just to write, k and n, they're all real numbers, okay? If you want me to be a bit more precise in what this rule actually means, let's use some negative values. So y equals x to the power of -3. Find dy dx. Exactly the same thing again. Put the power in front, write it as the coefficient, -3. Decrease the power by 1. Just remember, when you're subtracting 1 from a negative value, that's going to become -4, isn't it? Okay. So similarly, you could have the question written like that, you see. You should be aware that is the same as that, 1 over x cubed, okay? And this answer here is going to be written like this, so -3 over x to the power of 4, because that -3, okay, is basically -3 over 1, isn't it, if you run it as a fraction? And x to the -4 means it's 1 over x to the 4, so it's this, okay? It's just that, okay? Maybe the question you're given is written like this, in which case your method is to write in index form first, differentiate, and if appropriate, write your answer like that. Okay. This might be easier if you have to do something else with it, like if you have to set up an equation involving dy dx, or something like that. Okay. And lastly, let's just do another example. Now with this, you can't have too many examples, to be honest. Okay, let's do one that involves a negative value and a fraction. So y equals, and let's put a coefficient in front as well. Okay, let's make it a negative coefficient just to spice it up a little bit. Okay, so x to the power of negative 5 over 4. Okay, why not? That's not a bad one to do, is it? So dy dx is equal to, what we're going to get? Well, first of all, multiply that by that. Negative 5 over 4 times negative 4, so that's going to be positive 5, isn't it? 5 quarters times by 4 being 5, okay? And then x to the power of the negative 5 over 4, subtract 1. Whenever you're subtracting 1, just think about it as you're subtracting 4 quarters, okay? Because that's the same as 1, okay? So that's going to be negative 9 over 4. That's it. Okay, so they're really quick and simple. They're not really difficult to do, okay? So that's your main rule of differentiation. And I've used that term a couple of times now. If you noticed, maybe just play a video again, okay? Because sometimes you can never watch this video too many times, okay? And what I said was, what we're doing is we're differentiating that, okay? So see how quickly I've evolved from, in my first video, saying we're trying to find the gradient at this particular point, to suddenly now I'm saying y equals this, differentiate it, we get dy dx equals that. Just be aware throughout this whole unit of differentiation, when we're talking about differentiating, we're talking about finding the gradient at a particular point, okay? The dy dx, again as a reminder, it means the rate of change of y divided by the rate of change of x, or the rate of change of y over the rate of change of x, or how y changes depending on how x changes as well, okay? Or how y changes with respect to x, okay? Let's have a look at something else, okay? Let's have a look at what happens when you differentiate a numerical value, okay? So any number, let's just put 2. That's a nice number, isn't it? Okay. Y equals 2. What happens when we differentiate that? Okay. Well, I'm hoping you'll just think about what the line y equals 2 looks like. Okay. So here's a set of axes, not brilliantly drawn, but there you go. That's the line y equals 2. Can you see it's a flat horizontal line? Okay. Gradient of 0, isn't it? Okay. And that's going to be the same for any numerical constant. So y equals 3, y equals 7, y equals negative 2, y equals 0, y equals 1,000,000. They're all going to be horizontal lines. So the gradient of any constant value there is going to be 0, okay? Let's just look at why that is, okay? You could write it like this. It's not the best way of looking at it, but if you did, of course, the 0 times by 2, okay? The reason I don't like that approach is because it would be basically 0 times by 2, which is 0, and then what do? X to the power of negative. I don't like that bit in there, okay? It doesn't really make mathematical sense to me, that bit. The way I like to imagine it instead is that any constant value is a horizontal line, and a flat horizontal line's got a gradient of 0. Okay, so the simple case of when you've got just the, maybe just write it down, y equals k, then dy dx is just equal to 0. Let's just say where k is a constant. Okay. Now, that's pretty much all the rules you need for differentiation. Okay, let's just do some more examples. Okay, I'm keeping this there because I don't need much space for these examples. Okay, let's have a go at this one. Y equals x squared plus 3x plus 4, and we differentiate that. So what's different about it? You've got 3 terms in your function here. What, did you think functions only had 1 term? Of course they haven't, okay? This is a quadratic, okay? It's got 3 different terms, okay? You need to be able to differentiate things like this. Right, to cut a long story short, you just differentiate each term one at a time, okay? So we'll do that first, and then we'll talk about why that works, okay? So dy dx is equal to, differentiate that, 2x, okay? Differentiate that, so positive 3, because it's positive, plus 3, differentiate that, 0, okay? So that's when we differentiate each term one at a time, okay? Now, why are we allowed to do that differentiation, okay? It's because when we start off with this graph, y equals x squared, okay, we already know that the gradient function, the gradient at any point is determined by this, the x coordinate, and it would be twice x coordinate, it's 2x, okay? When we then change the graph by adding on 3x, we're now incorporating this linear function, okay? We're changing the original function x squared into this plus this. We're adding some linear variable, some linear function to it, okay? And we've got to consider how the gradient of that whole graph is going to change. How's the gradient of x squared change when you add 3x, okay? So the gradient changes by having this here differentiating to give you 3. Okay, so the gradient function effect is by having 3 there. And then when you have the plus 4 on the end, well, how does that change the whole graph? Okay, how does adding 4 to the end change the whole graph? It just moves it upwards 4 units. Okay, and if you have any curve and then just shift the whole thing upwards 4 units, you're not changing the gradient at any point. Okay, so we may as well add on 400 or 4,000 onto the end of that. It's not going to change the graph. Okay, so just going to move it up a lot more. Okay, so adding or subtracting any constant value does not change the gradient at all. What does change the gradient is any added variable you have to it. Okay, if you didn't follow that, fine. Okay, maybe you watch the video again, or you just go with a simpler explanation of you just differentiate each term one at a time. Okay, so like this one, for example, when we have y equals 7x cubed plus 3x to the power of 1/2 minus 4x to the power of -1 plus 7. Okay, not a nice looking function. Okay, but there you go. What I've done is I've just put together 4 different terms that make use of different powers of x. So I've got a positive integer there, a negative integer there, and I've got a fractional value there and a constant on the end. Okay, because that covers pretty much everything you can get in terms of differentiation. Okay, and the simple rule is you differentiate each one of these one at a time. So we'll start with that one. What is it? Yeah, that's going to be 21x squared. Then we do this one. What is it? So 1/2 times 3. So that's 3 over 2. And then x to the power of -1/2, decreasing the power by 1. And then this one here, -1 times -4, that's +4. And then x to the power of -2. And then that just becomes 0. We never write +0 because there's no point. That is it. Okay. I'm hoping you can see how far we've actually come. Okay, from my very first video, which took a long time to get through it, to get towards these key rules here, to being able to differentiate something like that. Okay, so I'm just going to reiterate, for any algebraic graph, remember this is all with algebra. Wait till next year when we start doing it with trigonometry and exponentials and logarithms. Oh, that's where it gets really exciting. Okay, this is just with algebraic terms. Okay, and you can see this rule here can be used to apply to any algebraic expression you can actually get. Okay, I'm hoping you found that useful, hoping that's helpful. My recommendation is just practice as many questions from the textbook. Okay, they should have answers in the back of the book somewhere. Any textbook you have should have answers. Okay, and the more of these you practice on, the better you're going to be. You're going to need it because, as I said right at the beginning, differentiation is the epitome of A-level mathematics. You cannot escape it. Okay, you cannot hope to get even a decent grade at A-level mathematics if you cannot differentiate. Okay, if there's one topic you need to know extremely well, it is differentiation. Okay, but also because it's a lot of fun, to be honest. Okay, I hope you enjoyed that, and I'll see you again.